Alright, so here are our 5 notes on solving special systems. Our objectives are to solve special systems of linear equations in 2 variables, which we've been doing, just not the special ones, and then determine the number of solutions in a system. So taking a look at this first idea here in a table, we've got our number of solutions, and this is what we've been doing up until now. We've had 2 lines that meet. Very exciting. So in that case, we're going to call this one solution, right? Because we've had this point where they meet. And then our description is that they have different slopes and may or may not have different intercepts. So we're not going to write that one. So then we have our special ones. So taking a look at what we have here, we have what they call coinciding lines, coincident lines, which are the same line, okay? And so if we have the same line, how many times does one line exactly on top of another line touch? And that's going to be infinite solutions. And of course we could use our fun infinity symbol. Alright, infinite solutions are going to come when the 2 equations have the same slope, and also when they have the same y-intercept. And then what we're going to be talking about a little later, we're going to have a true statement. Alright. So then we also have our parallel lines, okay? And when we have parallel lines, how many times do those things meet? Never. So there are no solutions for that one. They're going to have the same slope, right? Because that's what happens with parallel lines, same slope. But they are going to have different y-intercepts. And then in going with our true statement in the previous one, this one is going to have a false statement. And that's algebraically, we'll kind of talk about that in a second. So, our options currently for solutions to a system, a linear system, is one solution, which we've done up until now, infinite solutions because they happen to be the same exact line, or no solutions because they're parallel and so therefore they're never going to meet. Alright, so taking a look at our first example here, we're going to show that that has no solution. And so remember, no solution means that we're talking about parallel equations. Whoops, I just flipped the page. So how are we going to show that they're parallel lines? We can either go through and get the same slope and different y-intercepts, or we could actually solve them and find a false statement. So I'm actually going to do both just to kind of see what's happening. So the first thing that we're going to do is rewrite both of the equations so that they are y equals, something that we have been practicing. So taking a look at this first one, it's already y equals, and the second one, if I move this x over to the other side, we now have y equals x plus 3. And so from here, you should be able to say that if our system, whoa, that was a bad brace. Okay, so if our system includes y equals x minus 4 and y equals x plus 3, they have the same slope. Because your slope is 1, and different intercepts. One of them is -4, and the other one is 3. Alright, and so from this statement, we can conclude that we have a parallel line system. Okay, or we could go through and do our arithmetic, or our algebra, and that means that we would set them equal to each other. So I'm going to take x minus 4 and set that equal to x plus 3. And if I go through and solve them, maybe adding the 4 over to the other side, taking that positive x and moving it to the other side. Now you realize that you have 0, right, because these would cancel and these would cancel, equal to 7, and this is a false statement. So there are two ways, either algebraically or by looking at the formula itself, to identify if something is parallel. We can see they have the same slope, different y-intercepts. We can conclude they're parallel, meaning no solutions. Or we can actually go through the algebra and get a false statement and realize they're parallel, and so therefore they have no solutions. The answer, of course, is not that they have false statements, that it's a false statement. It's that they're parallel lines and therefore no solutions. So the next one here, we want to show that this has infinitely many solutions. And so, of course, we could go through and do it where we look at the equation itself, or we can actually get a true statement. So we're going to do both of those again. So taking a look at our second equation, it is not y equals yet. And so it's actually easiest if I just move this negative y over. And now I have y equals 3x plus 2. So that means that our system is this equation and this equation. And so hopefully you can see that they are in fact both the same. And so we'd be able to conclude they have the same slope, same y-intercept, and so they're the same slope, the same equation, meaning our solutions are infinite. Alright, or we can go through it algebraically, so maybe we are just kind of going through the steps and we didn't quite see that they're the exact same thing. We can go through our algebra and say, okay, 3x plus 2 is trying to equal 3x plus 2. And so we're going to maybe move our x's together. So I have a positive 3x, and so I'll move my 3x over. And that cancels, and I'm left with 2 equals 2. And that is a true statement. And so because it's a true statement, that means that they are the same line. And that means that the solution, or the solutions, are infinite. So we kind of get there the same way, alright? You either get that the solutions are infinite by looking at the equation itself, or by actually going through and solving. So, one caution is that if you ever get a true statement of 0 equals 0, some people will say that it actually means that the system has 0 solutions, but that's not what it is. Okay? So just because 0 equals 0 or 2 equals 2, that doesn't mean you have 2 solutions. That just means that you have a true statement and not indicating how many solutions, because it's actually infinite. So those are our notes and examples for 5-4, and so hopefully you get a little bit more about now we have one solution option, but also infinite and none for a system.